Okay, then you can go home. Right?
Yeah.
Revisit home. Everybody must be online today. So we'll get started. Let's see who we. Have some people online, good. So you all should have now gotten an email from Whitney with the Dropbox link. And I put a slightly modified version of the first set of lecture notes there and problem set 1. After class today at 2:30, we'll take a few minutes break and then have a problem session. And of course, you haven't had really any time to look at the problem set, but there's 2 problems in particular that are so critical that I want to walk through some of it with you, and then you can go back and do them in detail on your own. It'll be more of a tutorial than you telling me how you did the problems. One thing I did when I think the first lecture, we looked at this spectrum, and I pointed out that these 2 upfield shifted resonances, one was narrow and one was broad. And it occurred to me I should actually label them as to what they are. So the narrow resonance there is a methyl group, leucine 50, and the broad one is isoleucine 61, the gamma 1 hydrogens. So the isoleucine, that's a methylene group, and the leucine is a methyl group. So a lot of the line narrowing there comes from the 3-fold rotation of the methyl group, and that very fast dynamic process dramatically narrows the lines, which is partly why for very large proteins in solution, one does a lot of methyl experiments. But it also reminded me to say, realizing that this was an isoleucine methylene group, there's always 2 issues with dealing with and just looking at proton line widths. One is there's frequently a large number of unresolved scalar couplings that are broadening the line. So, I mean, you can see in the leucine that there's you can see a sign of a scalar coupling because the lines are so narrow. But for the methylene group, there's going to be a scalar coupling there to the other methylene hydrogens, since there's 2 methylene hydrogens. And if they're not degenerate, there's going to be a scalar coupling. There's also then a scalar coupling to the gamma 2 methyl group and to the beta hydrogens. So there's potentially quite a number of unresolved couplings here that also would be contributing to this apparent line width, not just relaxation processes. And then the other bit that I went back and did for you. Oh, the other thing about this is be relevant later on. I was actually surprised to find out that this was a methylene group because it shifted pretty far upfield, and we'll talk very briefly about chemical shifts today, and then later on, then of course, Anne will talk about chemical shift tensors in great detail. But for that to be a methylene group that's so far upfield suggests that it's subject to a very large ring current shift from some aromatic ring. And presumably, if we went and looked at the structure of ubiquitin, we would see what aromatic ring it's packed against. But certainly, understanding tertiary interactions in proteins, the hydrogen chemical shifts, there's a strong influence from the aromatic groups. That's more for the future. And then somewhere here, very far on. Right. I just said in words here that I like to think of the sample as composed of small subensembles, so that each subensemble has some magnetization, and then I can think about averaging over the subensembles rather than thinking about individual spins. And so I added a picture here in which here I imagine at equilibrium these little subensembles, and each subensemble has its own little bit of Z magnetization. And as shown here, they all add up because they all point along Z. And now we do a 90-degree pulse. And the critical point that I said is if we apply a Y pulse, that has to be a Y pulse everywhere in the sample, at least to a good approximation. And that's possible because we can generate a radio frequency field that's phase coherent over the volume of the sample, something that would be much harder to do at optical frequencies. And that means then that each of these, if we apply a Y pulse, each of my little imaginary subensembles in the sample see a Y pulse. So each of these Z magnetization gets turned into X magnetization, and then they add up together coherently to give a macroscopic X magnetization. So the appearance of the coherent transverse magnetization is a consequence of the coherence of the RF field when we apply a pulse to Z. Whereas if we had a huge dispersion in phase, so that the top of the sample saw a Y pulse and the bottom of the sample saw a minus Y pulse, then these little subensembles would tend to cancel each other, and we wouldn't generate coherent transverse magnetization. We would just generate a saturated system. And this is, if you think about a UV vis machine, where you generate the radiation from a lamp, and that means the radiation is coming from thermally excited electrons in the wire. There's no phase coherence between the electrons in one part of the wire and another part of the wire. So the phase of the electromagnetic radiation that is emitted is random, and therefore you can't generate X coherence on a conventional UV vis machine. All you would do is spread all the coherence into the transverse plane, which is what we would call saturation. So of course, on a UV vis machine, you can saturate the optical transition, but you can't invert it, for example, the way we can in an NMR machine. And if you want to do these kinds of optical experiments, then of course you have to go to phase coherent laser sources. Anyhow, those were the only two additions so far. It's always good as students if you find numerical errors to let us know. So we left off having done some simple things with 1D experiments. And just to finish this first set of lecture notes, as I said, Ann will come talk about chemical shift tensors. All I'm going to tell you now is that in what's called the principal axis system, the chemical shift tensor is diagonal, and we have three components then, sigma 1,1, sigma 2,2, sigma 3,3. for our purposes for the class, all we care about, I mean, for the part of the class that depends on isotropic chemical shifts in solution, we just need the trace of the tensor. So, or in this case, the trace divided by 3, the average of the tensor. So what we call the isotropic shielding is the sum of the 3 diagonal elements divided by 3. When we talk about relaxation, we'll be interested in delta sigma, as shown there, and then more in solid state NMRs, and I'll talk about, you can also be interested in the asymmetry eta. And what this means for us in solution is the real frequency isn't the Larmor frequency, what I've called omega naught. It's the Larmor frequency shifted a little bit by the isotropic shift. So that's shown here. And where'd my cursor go? Oh, there it is. So what you observe as the resonance frequency omega is 1 minus the isotropic shielding times the Larmor frequency, and what we call delta, the resonance offset, is also then adjusted. But I'll stop worrying about that. From now on, whenever I say omega, I really mean the real chemical shift offset for a particular spin that includes the shielding. And then probably anyone who's taken an NMR spectrum knows, oh, the cursor keeps vanishing. Knows that we don't really know absolutely frequencies usually. So NMR frequencies are measured relative to a standard. And so the standardization is shown below. We have the shift of a given resonance. We have the shift of a reference frequency, and we have the Larmor frequency for that spin. So that's the relative offset is the difference to the reference divided by the Larmor frequency. And since that's a very small number, that's multiplied by 10 to the 6th. A 6th is a million, and that's why frequencies are usually measured in parts per million on a spectrometer. And now there are IUPAC standard references for all the different nuclei. So for biological work, the reference in solution for hydrogen is DSS, which stands for some compound. So typically at some point, some DSS is added to a sample in order to get a reference. And then there are standards designed or designated for, say, carbon-13 and nitrogen. At least in most solution spectroscopy, we don't actually add those compounds. Instead, they're referenced indirectly. So we measure the absolute frequency of DSS hydrogens, and then there's a conversion frequency factor to get the absolute frequencies of nitrogen and carbon-13, and then we call those the reference frequencies for doing these calculations. When we talk about more practical aspects, you'll see some formulas. So again, here's the spectrum of ubiquitin, and now we know that the dispersion is caused by the chemical shift tensors, shifting the frequencies away from the Larmor frequency. And now up at BMRB, there's lots of data on the chemical shift ranges that you expect for hydrogens in carbons, etc. For the amino acids, there's somewhat smaller database for nucleic acid shifts because the nucleic acid NMR spectroscopists aren't as good at depositing their shifts. And you can kind of see if we look at isoleucine here, there's the gamma 1, and you can see that isoleucine that we saw for ubiquitin is shifted up here somewhere, quite an unusual shift outside of at least one standard deviation. So this is an idea of where the shifts are. Where the shifts are, what the coupling constants are, would be called the first order spectra, positions of the lines. The second order spectra is the widths of the lines, and we'll spend a lot of time talking about widths, but something, when we talk about relaxation, but more or less line widths in solution are strongly dependent on the overall rotational correlation time of the protein. So I've made some graphs here for different hydrogens. Hydrogen by itself, hydrogen connected to a nitrogen 15, hydrogen connected to a carbon 13. So the increase in each has to do with the dipole-dipole interaction between the hydrogen and the nitrogen, or the hydrogen and the carbon 13. One can estimate the tumbling time essentially from the mass for globular proteins. And then there's a program called Hydro that will do quite accurate calculations if you have a PDB file of the overall tumbling. And of course, one of the main parameters that comes out of NMR relaxation studies is the tumbling time. So one can go both ways. So if we had isolated spins, we're done. The Bloch equations are a complete description of an isolated spin 1/2 particle. But of course, we're interested in more complicated spin systems. So now if we have two spins, they're each spin 1/2, there are obviously 4 possible spin states. Both spins can be alpha, both spins can be beta, one spin can be alpha, and the other beta, or beta alpha. What the convention for two spins is to call one I and one S. So we say we have an IS spin system, and then the convention here would be that the first designation is for the I spin, and the second one is the S spin. So this is I spin in the alpha state, S spin in the beta state, so on and so forth. And if there are no interactions between them, then the energies are just the sum of the energies as shown over here. And then we can work out the populations of all 4 states. But that's boring. More interesting is when we have a scalar coupling between them in solution, or in solids, this could be we'd be talking about the dipole coupling. When we get to relaxation, you'll see that the fast tumbling of molecules in solution averages the dipole coupling to 0 in an isotropic phase. So the main other interaction that's evident is the J coupling. So now the energies change. So over here is now the expression for the energies. There's just the energy of the I and S spin due to the interaction with the magnetic field. And I'll sometimes call that the Zeeman interaction. And then there's the interaction due to the J coupling. And you can see the J coupling depends on the product of the 2 spin states, alpha being +1/2 and beta being -1/2. So now the energies of the 4 states, here's the energy of the alpha-alpha state, the energy of the alpha-beta state, beta-alpha state, and beta-beta state. And now you can see the energies are shifted relative to the case where J was equal to 0. So here's the spectrum we would see if J was equal to 0. The spins are independent, and we just see one line for the I spin and one line for the S spin, but it turns out the lines are doubly degenerate because this transition and this transition would have the same energy if J was 0. This transition and this transition would have the same energy if J is equal to 0. But now when we turn on J, this transition has a different energy than that transition. Similarly, this transition has a different energy of that transition, depending on the relative signs of J, because J could be positive or negative. But now these degenerate states split, and now the I spin shows a doublet and the S spin shows a doublet, separated by J in hertz, or 2 pi J in angular units. And again, you took organic chemistry and saw NMR spectra in organic chemistry, you see a lot of these multiple patterns. So we need a theory that accounts now for evolution in a 2-spin system with some coupling between the spins. And in solution, that coupling will be the J coupling usually, but in solid state or in partially aligned median solution, that could be the J coupling plus the dipole coupling. So what we have to do next is develop a mathematical theory that accounts for this extra complexity. And eventually, we would like to work that theory down to something that looks as much like the block equations as possible, because a lot of our intuition comes from the block equations. The question is, how many mathematical things do we need? So if we go back to just the single spin, we have IZ magnetization, IX magnetization, IY magnetization. So it looks like we need 3 mathematical objects to describe the single isolated spin, but we left one out because Z magnetization we saw comes from the difference in populations between the alpha state and the beta state. But there's also the sum of the populations. But the sum of the populations is a constant that we'll call identity. We can't change the number of spins in our sample. They can be redistributed between the alpha and beta states. But if we change the number of spins, we blow up the spectrometer in most of Manhattan. So that's not going to happen. So we need 4 things, even though one of them is trivial. We need 4 for 1 spin. So how many for 2 spins? 16. I mean, you might have guessed 8, the sum or the product. It had to be one of the 2. And it turns out we need 16 mathematical quantities. And if they were all capable of interacting with each other, that would lead to a network of 16 times 16 interactions, which is 256. So fortunately, most of those will be 0 in practice, but you can see the complexity gets to be large very quickly. If we go to 3 spins, we need 64 mathematical quantities, 4 cubed. And then 64 times 64 must be getting close to 1,000 possible interactions. And mathematically, these, just like the block equations, can be represented as a 3 by 3 matrix. In principle, our 2-spin system can be represented as a 16 by 16 matrix. And already, I don't like thinking about that. And if we have 3 spins, then we have a 64 by 64 matrix. And I never even want to write that down by hand. So humans are really bad at thinking about matrices. Humans are good at thinking about symbols. So we're going to derive basically a symbolic representation of the matrices. Of course, fundamentally, it's all going to be a matrix. And when we get stuck about what the symbols mean, we can always go back to the matrices. And if it's a big matrix, we can turn the problem over to Mathematica or Python or some other computer program to do the work for us. In some other part of the galaxy, it could be that NMR spectroscopists have evolved in which they're really good at thinking about matrices, and they would find thinking about the symbols to be really crazy. But here, in our corner of the universe, symbols are what we like. So as much as possible, we'll show the matrices, but then give them symbols. To do this, we're going to start by developing a quantum mechanical representation of the NMR experiment, and then turn that, as I said, go back to a symbolic representation. And that means we have to go to the next slide deck. But because it's fundamentally a quantum mechanical description, it will also turn out that these symbols that we invent, which wasn't necessarily didn't necessarily have to be the case, but Richard Ernst and others, groups who thought up this symbolic representation, thought up the symbols in a way that the symbols match the things we observe in the NMR spectrum. So it's not only that we get to replace the matrices with symbols, but the symbols have a direct connection to doublet components, multiplet components, the lines you see in NMR spectra, the relaxation, the coherences that are connected by relaxation terms. So it's really kind of a remarkable description that links the observables in NMR spectra to the symbols to the quantum mechanics. Also means that NMR is the best way to learn quantum mechanics, because everything you do mathematically in quantum mechanics, you can then go run an NMR spectrum and see that the predictions are correct. Anyhow, once we develop the quantum mechanics and have the symbols, we're going to forget about the quantum mechanics. And that means for anyone in the class who hasn't had previously a quantum mechanics course, you can kind of drink coffee and follow along, but you won't need to know this in great detail to go on with your life as an NMR spectroscopist. Because again, once we know the symbols, we don't need this part anymore. But here is the Schrodinger equation, the starting point for quantum mechanics in energy units. But most of the time, we don't want to think about energy units. We want to think about frequencies. But of course, we can always get an energy from a frequency, because energy is h bar times omega. So I'll drop the h bar. That's equivalent to say I work in a unit system where h bar is equal to 1. And when you want to switch back to an SI unit system, you have to figure out by unit analysis where all the h bars go. So the h bars will mostly disappear. So if h bar is equal to 1, here is the Schrodinger equation, and script h here is the Hamiltonian, and The Hamiltonian from physics is the operator for kinetic energy, the operator for potential energy. For us, that's going to mean we have H naught, that's the Hamiltonian for the big magnetic field. H1 is the Hamiltonian for the RF field we turn on to make pulses, and H local is everything else. And for a while, that will just be J couplings and chemical shifts. In the language of quantum mechanics, this capital psi is called the wave function or the state function, and it contains information about the state of the system, and H contains all the physics, as I said, the interactions with the magnetic fields, the local interactions. The interpretation of the wave function is that the wave function times its complex conjugate is the probability that we find the system in some state at time t. So while the wave functions can be complex numbers, probability then will always be a real number. Just a few details. A properly normalized wave function has the property that if we multiply the wave function by the complex conjugate and integrate over all the coordinates of the system, we get 1. If that's not true, we can always normalize the wave function by dividing it by the square root of whatever that integral was. And when we go on in NMR, frequently the wave functions that we use aren't going to be normalized to unity, because then you end up with a lot of square roots of 2 running around. Mostly for us, it'll be okay if all the wave functions have the same integral, even if it's not 1. But sometimes you have to pay attention to that. So that's just kind of a warning. And I'm going to tell you some facts. I don't want to derive a coursework of a semester-long course in quantum mechanics here. If the wave function is independent of time, then we can solve the Schrodinger equation by a technique called separation of variables. And in energy units, the wave function is a function of time, is a wave function that's independent of time, where tau here refers to all the other variables in the system other than time. And then a complex phase factor that depends on the energy divided by h bar, but energy divided by h bar is just a frequency. So we have a time-independent wave function multiplied by a wave function, by a complex factor. And of course, if we calculate probabilities, we multiply the wave function by its complex conjugate. So this phase factor is going to disappear when calculating probabilities, which again is a good thing because the probabilities have to be real numbers. The energy of the system then in quantum mechanics is calculated by this integral, where now we have the Hamiltonian inserted into the middle here. One interprets this as the Hamiltonian acts on this wave function psi. The result of that is multiplied by psi star and then integrated. And then I have to tell you, what do I mean by the Hamiltonian operates on the wave function? So depending on the math classes that you've taken, you might not have ever heard of an operator before. So an operator is something that acts on a function to give a new function. hopefully if you took algebra, you're all familiar with functions. A function is something that acts on a number to give another number. So squaring, right, is a function that acts on a number and gives you a new number, the square of x. So here, this is a step up. An operator acts on a function to give a new function. Later on, we'll learn that there are super operators that act on an operator to give another operator. And that'll be enough for us if you take a graduate course in abstract algebra. Of course, this process continues up to infinity. So then, as an example, we might define an operator A that takes the derivative with respect to x. So then I understand A operating on the function f of x to be the derivative of the function with respect to x. And then I just apply the normal rules of calculus. So this symbol d dx doesn't really have any meaning until I operate on a function written to the right. Sometimes you'll see we have operators that can be regarded as operating either to the right or the left, and there's a whole lot of mathematics about that that we mostly won't have to worry about. So just an example, suppose our function was e to the lambda times x, then a operating on f of x is the derivative of e to the lambda x dx, and the rules of calculus say that's lambda times e to the lambda x. And sort of remarkably, that's just lambda times our original function. When this happens, that's very special to us. So here we have an operator that acts on a function, and it gives back a number times the original function. In that case, f is called the eigenfunction of the operator. So the exponential turns out to be the eigenfunction of the differential operator. And that's it. Something like if the function was f squared, the derivative operator acting on x squared gives back 2x, which is not the same function. So x squared is not an eigenfunction of the operator d dx, even though we can use it. We can operate on the function x squared. We can operate on the function sine of x, right? The derivative of sine x is cosine or minus cosine x, and that's not an eigenfunction, even though it's a perfectly legal mathematical operation. So the eigenfunctions are special, and as you'll see, we'll be interested in them. And then the number lambda here is called the eigenvalue. In the language of mathematics, this comes from some German that I don't know. Now, we want to measure things. You want to measure the NMR spectrum. And everything that can be measured is called an observable quantity or a measurable quantity. And these have to be real numbers. You don't have meters in the lab that give you imaginary numbers. Even in NMR, when we think there's an imaginary quantity, it's because we constructed two real numbers to make an imaginary number for our convenience, not because we had a detector that measured imaginary numbers. So observable quantities are real, and there's a principle in quantum mechanics that every measurable quantity has associated with it an operator that's Hermitian. And Hermitian operators have this property that the operator is equal to its adjoint, and the adjoint is the transpose conjugate. You'll see in a bit too that all operators have associated with them a matrix, and it's easier to understand than what I mean by a Hermitian operator, because its matrix representation is equal to the transpose complex conjugate. And that's easy to see for a matrix. I just transpose it and change all the i's to minus i's, and I get the same original answer. It also has this kind of integral relationship that I won't go into. And then there's a formula in quantum mechanics that says, if we want to know our measurable quantity, the result of some experiment, shown here is the ensemble average of A, then we have to form, again, this kind of sandwich where our Hermitian operator is in the middle. We operate on psi, multiply by psi squared, integrate over all the coordinates, and we have our measurable quantity. Again, formally in quantum mechanics, this averaging A in the angled brackets would mean the ensemble average, meaning the average over lots of different dynamically prepared systems. That's a little different than we want. We want the average over a Boltzmann distribution. So again, if we were doing molecular beam experiments in a PChem lab, we might be done. There we can prepare isolated systems in the molecular beam. Here's the equation we need. We need, because we're doing NMR in solution at more or less room temperature, we have a Boltzmann distribution, and we need to take that into account. We don't have identically prepared systems. We have to do some thermal averaging. And now just a few more details before we get onto the problem of the thermal averaging. Hermitian operators have a lot of really fantastic properties. By the way, if the operator was real, if its matrix representation was real, what kind of matrix would it look like? It would be symmetric, right? So for real matrices, the correspondence to a Hermitian matrix is a symmetric matrix. This is a point of interest. So if we have this Hermitian operator, right, it's going to operate on functions and give back other functions. So it may have eigenfunctions, just like d dx as the exponential as an eigenfunction. Hermitian operators may have eigenfunctions, and in fact they do. And they have the property that they're orthonormal to each other. So if we take two different eigenfunctions of a Hermitian operator, multiply them together and integrate, we get 0. If they're the same, we get 1 because the wave functions will be normalized. So that's a very important property. And they're also, the functions are complete in the sense that we can represent any arbitrary function that observed the same mathematical boundary conditions as a sum over, I really don't understand why I keep losing the pointer.
It's on the left.
Pardon?
The cursor is on the left side, so.
There we go.
Yes.
In the sense that any arbitrary function can be represented as a linear combination of the eigenfunctions of the operator times some weighting factor. It'll be a complex, most generally a complex number. And there's a rule for finding the coefficients. I think I'll skip that for right now. We'll come back to it. But here's just a simple example if you've never seen this before. So the particle in a box wave functions. So we have some function defined over the range 0 to 1. and the orthonormal wave functions are just sines, as shown here. I've just taken something from the, from quantum mechanics. You don't have to worry. But it turns out that these sines, if I change n, the different functions are orthonormal to each other. I can show that if I do the integration, that I get 0 unless the two are the same. So here in blue is just some function I made up. It's a cubic function with arbitrary coefficients. I just made it up to have some arbitrary function. And it has the same boundary conditions as the sines. It's 0 here and it's 0 over here. Here's the first function. Obviously, if n is equal to 0, I get 0 because sine of 0 is 0. If n is equal to 1, you can see that's just the first lobe of the sine function. If n is equal to 2, I get a full cycle of the sine function. So what's shown over here is I've tried to find the best approximation to the blue function using just sine with n equal to 1. And you can kind of see that's the best I can do. And, I got this number from the numerical procedure that I clicked by on the previous page. And here I've taken the first two. So n equals 1 and n equals 2. And I've done the mathematical analysis to find the best superposition. In that case, I have these coefficients. And you can see the approximation is pretty good. And here I've taken the first 5 sinusoids, and now I have a really very good approximation. And of course, as I continue this, the approximation gets better and better. So this is very general. It's just that as we go forward, we'll have different sets of basis functions depending on what the particular problem is that emerges from whatever particular Hermitian operator we have. And there's whole sets of these that exist in the mathematical literature. These sine functions are actually related to, I think, Chebyshev, what are called Chebyshev polynomials. We'll end up making great use of expansions in what are called spherical harmonics. The spherical harmonics are functions of two angles orienting a vector in three-dimensional space. We're very interested in rotations in three-dimensional space in NMR spectroscopy. So the spherical harmonics will emerge over and over again as a set of orthogonal functions that we can use to represent other functions in three-dimensional space. There's an old joke, and there's actually a paper about it, that with I think it's the paper says, with 5 coefficients, I can approximate an elephant, and with a 6th coefficient, I can make its trunk wag around. So I'll also get tired of writing these integrals all the time. So Dirac thought up a notation to represent the integrals in a much more compact fashion, in which the wave function here on the right is represented by the wave function with this kind of angle bracket, and the complex conjugate is represented by the reverse. And that means, for example, these expansions are a whole lot simpler. So my unknown function is a linear combination of all of the basis functions. He called the wave function that is vertical bracket, angle bracket, the one on the right, was called the ket, and the complex conjugate is called the bra. So when you put them together, you get a bracket, a bracket. Sometimes you get famous in science by inventing cute names. So then in the Dirac notation, here's an arbitrary function expansion. We have our arbitrary function says we can expand an arbitrary function into a linear combination of some eigenfunctions. And sometimes I'll call the eigenfunctions a basis functions. And the sense that this set of basis functions is the complete set for expansions in some space. So let's go back. Here's our expression for calculating our expectation value, our observable quantity. It was psi A, psi star integrated. In the Dirac notation, this would be these brackets, the ket, the operator that acts on the ket, and then the bra. And now the brackets, of course, implies that we're doing the integration. And if I substitute in for the expansions of the ket and the bra, the ket is the sum over n, c sub n times the kets associated with the basis functions. And the complex conjugate, I have the bra, another index, but now the complex conjugate of the expansion coefficient. And to get the complex conjugate, I have to take the complex conjugate of everything in the equation. Now, the cute trick then is to say, here I have something with two indices. Here I have something with two indices. Why don't I imagine this product in the same form here? So I've invented an operator P and said that the result of P operating on the ket M integrated over the bra N are these two numbers, Cn, Cm star. And this then is called a projection operator. And you can see here then that this product is something with two indices. A number with two indices I can think of as being an element in a matrix where n is the row and m is the column in the matrix. So this operator, anyone see where the cursor went now? Oh, there we go. So this operator, when I do this, gives me a two-element number that I think of as a matrix element. So this operator has a matrix representation. It can be represented as a matrix, all combinations of these indices. But similarly then, this must have a matrix representation. The result of this is a number. That number has two indices, m and n. And if I take all combinations of m and n, I fill out the matrix. So the operators all have matrix representations, and that's shown here. But now I have the product of the matrix elements summed over all possible elements. And the sum over m, right, is just the product. If I take two matrices, when I multiply them together, I do the sum of rows over times columns. So this first summation is just the product of P times A. And then I'm left with the two outer indices, the n's. But that just says I take the product of the matrices and sum up the diagonal elements. And the sum of the diagonal elements of the matrix is called the trace. So in this Dirac notation, the observable, the expectation value or the ensemble average of A is just the trace of this projection operator times the Hermitian operator for the observable quantity. So a very compact expression, and of course, we all like compact expressions. It turns out, though, that this is more useful than just manipulation of these symbols. And that's because, again, we want to thermally average. And one way we could do this, right, is redo the calculation for each individual member of the ensemble and then average them together. That's really painful, right? Even if I said I divide my NMR sample into sub-ensembles that behave the same and each sub-ensemble has 1,000,000 spins in it, I still have 10 to the 11th ensembles. And I don't want to do this calculation 10 to the 11th times and then average up the results. Certainly, I don't want to do it by hand. Maybe on a computer, I don't care. That's only the computer's time, not my time. But if I'm trying to do anything myself or get to any kind of analytic results, it's painful to do the calculation 10 to the 11th times and then do the averaging. And the remarkable thing that we'll do next is that we can average first and then do the calculation, the quantum mechanical calculation once. So here's the idea. We want the Boltzmann weighted result. And that would say we take each possible psi in our sub-ensembles, calculate the expectation value for each sub-ensemble, and then average by the probability of each sub-ensemble. Right? That's a very straightforward way of doing things and integrate over all the probabilities. That's what I said is the straightforward approach. For each sub-ensemble, we calculate the observable quantity, and then we average over the 10 to the 11th ensembles. Life is a little easier because many of those sub-ensembles will have the same probability, so we can lump them together, but we still have a complicated integration. So now let's switch to the Dirac notation, where we have these coefficients, C sub n and C sub m, and we have the calculation of the operator acting on the different wave functions. This does not depend on our particular Boltzmann distribution. The operator A is just the operator for the observable, and M and N are the eigenfunctions. Those are the eigenfunctions of the operator, so they're calculated once and they're the same eigenfunctions forever. What changes as we go from one system to another is how the eigenfunctions get weighted together. That's all in the C's. When we do the expansion, the eigenfunctions for one are the same. It's the weighting functions that determine how they're mixed together to match our particular function. So when we think about the different Boltzmann distribution, that's contained in the C's, not in the A's. So when we do the averaging is just over the C's. The bracket there, M-A-N, those are something you just do once. So now that means I have some operator that's the average of this projection operator. And I'll call that the density operator, sigma. So all the Boltzmann averaging gets buried into sigma. And then we don't have to do the 10 to the 7th. If we know how to calculate sigma, we're done, or the 10 to the 11th calculations. Now, there's one bit of complexity or notation here that one should be careful of. This is what we've gotten so far. This density operator would be the density operator for the whole system. We're mostly going to care about what's called the reduced density operator. The density operator subtracted away from the identity operator. Remember, when we looked at the populations of, say, the alpha and the beta spin state are just marginally different from a half. So, and we don't really care about that half population of each of the two states that adds up to be the identity, because it's going to be there forever. So the reduced density operator is the deviation away from unity, from identity. I should probably at this point use rho instead of sigma to indicate the density operator for the whole system, and then later on define sigma as the reduced density operator. So I'm being a little lazy here. When you look in the literature, you have to pay attention to somebody talking about the full density operator or the reduced density operator. And while I said I should use rho and sigma, there's also not, particularly in the early literature, any real consistency about that difference. Now, mostly people use sigma to represent the reduced operator, the one we actually care about for analyzing experiments. But you do need to be careful when reading the literature, particularly the older literature. But what this means in practice is we don't care about the wave functions so much, we care about sigma. So we'd like to have an evolution equation for sigma, because if we knew sigma at each point in an NMR experiment, here's our recipe. Then for calculating the Boltzmann weighted observable, we take the trace of our operator A acting on sigma, and then we know the result of a thermally averaged NMR experiment. So we need, for any observable, eventually we have to know what A is for an NMR experiment, but then we need an equation for sigma. And what we have to do is convert then our wave function view. We have an equation for the wave function. We have to turn that, the Schrodinger equation, into an equation for sigma. So in Dirac notation, here is the Schrodinger equation. I've replaced sigma, I've replaced psi with its expansion in some basis functions. And the basis functions don't depend on time. So the derivative applies only to the coefficient C. And over here on the other side, I have H acting on the wave function, but numbers don't matter. They commute and they can come out front. So that's just d psi dt is equal to minus I H psi put into the Dirac notation. And my trick in these situations is always to multiply both sides by a bra. So here I've multiplied by the bra k, some other basis function. I've multiplied on both sides. Again, numbers commute, so I can move it again to the outside. I have to be careful. Things that are matrices don't commute. So I always have to pay attention to whether I'm allowed to commute things, but numbers always commute with everything else. And the C's are just complex numbers. And now I take advantage of the fact that the basis functions are defined to be orthogonal to each other. So the integral is 0 unless k is equal to n. And that means the summation collapses to only the k term. So I have the derivative of this coefficient c sub k with respect to time is equal to all of this on the other side. And that's why this orthonormal property is so important to us, because I can always play this game, pre-multiply, integrate, and some of the sums will collapse. So what I'm interested in working out is a differential equation for one of the matrix elements, one of the elements in the matrix for this density operator. Because if I can work it out for one element of the matrix, I can work it out for all the elements of the matrix. And remember then, the matrix element is the Boltzmann average of C sub k times C sub m star. And the derivative of a product is the product of the derivatives. And averaging commutes with all of this. So I end up with just applying the chain rule of calculus and with my lost cursor. Oops. Oh, we really jumped along. So here's the derivative. I don't know why I did it in this order. Here's the derivative of the second term plus the derivative of the first term. So just applying the chain rule of calculus and on. Then I substitute in for each of these. So I've substituted in that I know this, that came here, is the derivative of one of these is equal to all of this. So if I need the derivative of the complex conjugate, I have to take the complex conjugate of everything here, and the complex conjugate of C sub n is C sub n star. The complex conjugate here, I make use of the Hermitian property, and it ends up the complex conjugate just moves the n over to be the bra and the k to be the ket, because the complex conjugate transpose of H is itself. So I replace this side with then that result complex conjugate of, I messed up. I think for a moment if I messed up the notation.
Second line is
Okay. I think I'm okay. I'll have to double check. I think it's okay. So that's the second line. And then there is a trick that can be used that the ket ra written here is an identity operator. And once I insert that identity operator, I can then do the sums over n, and this collapses all of this to the product sigma times h, and then calculating the matrix element, and on this side, h operating on sigma, again, the matrix element. And I can write this sigma h minus h sigma is called a commutator in quantum mechanics, and is given this symbol, h comma sigma. So I end up ultimately, and again, at this point, you can forget the math. This is the corresponding equation to the Schrodinger equation, but now for the density operator. This is called the Liouville von Neumann equation. And it says d sigma dt is minus h commutated with sigma. So if I can solve this differential equation for some initial condition, for example, the equilibrium density operator when my sample is in the magnet and all the magnetization is on Z, starting with that initial condition, if I know how to solve this differential equation, then I have sigma as a function of t through my NMR pulse sequence. And then if I know the operator A that's associated with detecting the free induction decay, I'm done. I then have a recipe for calculating the free induction decay. After that, it's all math. I Fourier transform the free induction decay, et cetera. So in principle, we're done. We just have to figure out what the equilibrium density operator is, because if we solve a differential equation, there's going to be some initial condition, right, that we have to start with. Our initial condition will be the equilibrium density operator. If we know how to solve this equation, we can then take that initial density operator and propagate it forward until we record the NMR experiment. As it turns out, we'll tend to do this in pieces. We'll figure out how to solve the Liouville von Neumann equation for a pulse. So we'll start with the equilibrium density operator, apply a pulse, and now we have the equilibrium density operator associated with, for example, X magnetization. And now we're going to let that X magnetization evolve, and we'll have to figure out how to solve the Liouville von Neumann equation for a free precession Hamiltonian in the absence of the RF field. But what's important relative to the block equations is we can solve this equation for chemical shift plus J couplings. So we can generalize. And then we can apply another pulse, calculate the density operator after that pulse, more precession, whatever we need to do, all the way through stepwise, pulse, free precession, pulse, free precession, until we turn on the receiver. And at that point, we take the trace with the observation operator to find out what the FID looks like. So we break a very complicated pulse sequence up into individual blocks where we know how to solve the Liouville von Neumann equation, and then eventually take the trace with the density operator. So in principle, we're mostly done. A lot of complications, there's still some complications to go, but in principle, our path is straightforward. Now, the Schrodinger equation, I'm just going to give some hints or roadmap to what we do next, just to finish today. The Schrodinger equation had a simple solution when the Hamiltonian was independent of time. It will turn out next class that the Liouville von Neumann equation has a simple solution when the Hamiltonian is independent of time. That shouldn't surprise you because the Liouville von Neumann equation came from the Schrödinger equation. And all we did essentially was do some averaging over a Boltzmann distribution. And the Boltzmann distribution is independent of time. So we also should have this similar result. But it will turn out that in many cases, our Hamiltonian is not independent of time. For example, when you turn on a pulse, the RF field is modulated in time at the frequency of the radio frequency of the pulse. So that's a problem. We could figure out how to solve the Liouville von Neumann equation for a time-dependent Hamiltonian, except in special cases, that's extremely complicated or not known. So that's not our usual approach. Our usual approach is going to be to do a frame transformation. You already saw that when analyzing the block equations, we switch to the rotating frame. If we switch to the rotating frame that is rotating at the same frequency as the RF field is modulated, then the RF field looks stationary and it doesn't have any time dependence. And then we can switch back if we need to the original frame. So that's going to be the same trick here. When we have a Hamiltonian that depends on time, we're going to switch to a frame of reference that makes the Hamiltonian look independent of time, solve the Liouville von Neumann equation, and then switch back to the original frame of reference. So we'll need to find out, after we see how we solve the Liouville von Neumann equation for a time-independent Hamiltonian, we'll then have to see what kind of transformation will take a time-dependent Hamiltonian to a time-independent Hamiltonian. And then when we have more general Hamiltonians, that instead of being called the rotating frame transformation, it'll be called an interaction frame transformation. So then we'll need to work out what does the Liouville von Neumann equation look like if we do a frame transformation. And that's kind of the last of our sort of complicated mathematics, because then we have a recipe. Start with equilibrium, density operator. If necessary, transform into an interaction frame to make the Hamiltonian look independent of time. Solve the time-independent Liouville von Neumann equation in the interaction frame, transform back to the lab frame if we need to, and just iterate that process all the way through the pulses. And that'll be our final recipe. In solution NMR, it's pretty much just the pulses that require this transformation because the scalar couplings and the chemical shifts are independent of time. So we don't need to do a transformation for them. When you get to solid state NMR, of course, it's a little more complicated if you're doing MAS. Then you have time dependence due to rotation of the rotor and time dependence due to the pulses. But the idea will be the same. It'll just be more frame transformations until you get to a frame that is independent of time. Now, if we can't find, yep.
I think the last class you had talked about an M plus quantity, which was MX plus IMY detection quantity.
Right.
From the look of it, it does not look Hermitian.
Right. And this is a funny detail because, of course, we form that in reality by measuring the X magnetization and the Y magnetization and combining them to look like a complex number. We shouldn't be able to measure the X and the Y magnetization because that should violate the Heisenberg uncertainty principle. But the violations of the Heisenberg uncertainty principle scale as 1 over the square root of the number of particles. So when we have 10 to the 17th particles, the violations of the Heisenberg uncertainty principle are not important. So that's actually a funny thing, because basically we use this quantum mechanical theory to explain a result that is basically classical. And it just turns out, for a reason I can't explain, it's easiest to think about the experiment using this quantum mechanical formalism, even though at the end of the day, what you measure is essentially a classical result. Anyhow, I think we'll stop there for the lecture part today. We'll take a 5-minute break. And as I said, for the problem session, I want to walk through a couple of the problems that I think are particularly important. And I'll probably need the 5 minutes to remember how I switch cameras. This lecture is now posted on the Dropbox, by the way, so you can review what we've done if you want to go through the algebra in great detail.
No, you need to use your. It's some. It's some. Something.
Cameras. Ooh. Now we've lost the zoom from this camera. Did they take the remote away? We seem to have lost the zoom. Yeah, that happened. Yeah, that didn't happen the other day when I switched.
You got the copy. They could now.
Okay, great. We're taking a short break while I get more coffee.
It's not falling in there. It's sitting. Probably something else. Yeah, let's make sure. Oops. Better. Yeah. Slightly additional maybe. There's additional sentences. Yeah.
It's also graph and also bind, organizing, and also submitting the papers, and also writing the paper, and also he's now the.
So we'll get started again at 2:40 for those who are online. So you have 3 minutes to get coffee.
He's now the associate.
Oh,
More working on the other yeah. He said that, but yeah. Anyways, he's so mean. So maybe you can send him again. Yeah. It is.
And by the way, everybody online, with a minute, I mentioned matrix, had a cringy feeling back from high school algebra. I'll post some refresher information about matrices in the Dropbox.
That would be great. One. I promise. With us.
And those of you with very generous PIs like Ann and Hashim, I'll post a link to an inexpensive, extremely nice mathematical review textbook written by a good friend of ours named John Straub. And your PIs should have many copies sitting around the lab.
that a review of mathematical techniques?
Mhm.
Okay.
Focused really on biological sciences
Oh,
and chemical sciences, as opposed to a general mathematical review. So the first problem, super trivial, but one has to do this over and over again. So let's just do it. So X, Y, Z. Can anyone see that online? Seems awfully blurred out. Let me see what I can do.
It's
It's
pretty,
barely visible.
What's that?
It's just barely legible. I think it would be better if there was no glare from, if you just change the angle of the board.
Okay, well, we're trying to figure out,
Didn't help as much as I thought, sorry.
which light is causing the problem. Not that light.
Perfect.
That's better.
Oh, yeah.
Wonder if it's light from,
I think this light is the
You
one.
able to turn that off too?
I think this monitor light itself is
Are you-
making the
Monitor itself.
monitor itself is the light source.
this.
I think this.
This is what is clear as it get to see it.
That doesn't seem to do anything. Oh, that stays on though.
The projector.
Does the projector have a blank? We don't need the projector.
You're not really need it at all. I can turn it off.
Yeah, at this point, we don't need it. Let's see if that helps. Yes, that's better.
It's very.
Oh, but you guys can't see. Now we gotta have some lights so that people in the room can see. That takes.
I can.
That's here. There must be one of these that you guys need.
Yeah, that one.
Now let's try turning them down a little bit.
One more.
Okay. Yeah, that bleached it out completely.
Maybe we can see from here.
Oh, that's true. Now this light, I think, has to go off.
Oh.
Yeah.
We see from here.
It's also, it's fine with it.
Okay. Wonder what the thing on the side is.
Sorry, which one?
There's some glare on the side. I'll just stay away from it.
Yeah, where is that coming from? Oh, the, window.
Okay. I think there's nothing.
No, nothing glaring.
No, it's monitor, I think.
Yeah, the monitor.
That, the computer?
No, this monitor.
Ah, okay.
This is TV
Okay.
screen. Yeah.
Ah,
Anyhow, so the first problem, or actually problem number 3, I think, just says we're applying a wide phase pulse at 25 kilohertz. And again, that's really our measure of amplitude. The frequency is on resonance with the pulse, with the spin. That just means the pulse has an amplitude that's going to rotate magnetization at 25 kilohertz. And the first question is, on resonance, where does the magnetization end up? And our rule is thumb is along the magnetization, finger or along the B1 field, fingers on the magnetization, and then we're going to rotate by 90 degrees. So here, starting on Z, on Y, a 90-degree rotation is going to put the magnetization onto the plus x-axis. And again, when we're going to do that kind of transformation 1,000 times during the semester. And then the question is, how long is the pulse? And that's the main point of this problem, because that's also going to happen. A calculation you do your entire life as an NMR spectroscopist. So one way of thinking about this then is if something is rotating at 25 kilohertz, it's always the time times the frequency is equal to an angle. So we have a frequency. The question is, how long is the pulse to get a rotation angle of alpha? In this particular case, alpha is 90 degrees. The frequency is 25 kilohertz. What is alpha? Do I put 90 here? Do I do pi over 2? I put 1/4. And why 1/4?
Because it's 1/4 of a full. Like I can't use angles here because I'm not using angular thing.
Right, and this was a completely confusing part of NMR, is you're always switching back between hertz and angular units, omega versus nu. Right, so omega is 2 pi nu. And it's natural when doing the theory to think of in angular units omega, particularly when we get to relaxation. But the spectrometer is normally showing you nu. So, and that's hertz. And hertz means 1 per revolution per cycle. So 90 degrees is 1/4 of a cycle. So if we're working in hertz, alpha here has to be 1/4 because it's 1/4 of a cycle. If we converted this to omega, then we would have to multiply by 2 pi, and I would have 2 pi times 25 times 10 to the third times tau is equal to 2 pi times 1/4, which is pi over 2, right? Which is the right measure of 90 degrees if we're talking about angular units. So the two representations are completely consistent with each other. Either if I'm thinking in hertz, my rotation angle is 1/4 of the cycle. If I'm thinking in angular units, 90 degrees is pi over 2. Most of the time when you're sitting at the spectrometer, you're thinking in hertz. And in this case, then, we solve for tau is 1/100 times 10 to the third is, I think, 10 microseconds for the 90-degree pulse. So to get the 90-degree rotation, we turn on our pulse for 10 microseconds. If we wanted a 180-degree pulse, we would turn it on for 20 microseconds. And then, of course, a practical question, if you're sitting at the spectrometer, is how do you know if you have an RF field whose amplitude is 25 kilohertz? It could be that you went and asked Shabani, what's the pulse length? But quite commonly, one measures the pulse length. It'll vary a little bit depending on how salty your sample is, etc. But the pulse length, the same sample, if you're bringing the identical sample to the same spectrometer to do another round of experiments, the pulse length for a 90-degree proton pulse, for example, should not vary by more than a fraction of a microsecond. If it does, either you've mistuned the probe or the probe is broken. So it's a very sensitive diagnostic of the health of the machine or your ability to tune. And there's lots of ways of measuring the field strength. A simple one is to sit on resonance with some isolated spin and apply a short pulse, phase the spectrum, and now lengthen the pulse. And when you hit 90, you'll see a maximum. When you hit 180, you'll see inversion. When you hit 360, you'll see a null. And inversion will be a null, and then the next null will be 360. So you search for the 360-degree null, and 1 over that amount of time, then is field strength. That's the kind of calculation one does practically. If you go ask Shivani, that's basically what she has done as well. But these calculations are very practically important, but also one does in theory all the time, but also reminds us this confusion that will happen over and over again about hertz versus angular units. Okay, so but the problem I really wanted to do or get started on today is so on resonance again, we have a field strength of 25 kilohertz. So we know now that the 90-degree pulse on resonance is 10 microseconds. I forget what phase I said in the problem, maybe I didn't say.
Which is the problem number?
This will be problem number 4.
Like this.
Y phase.
Yes. Duration is 10 microseconds.
I'll see where I say Y phase.
A second sentence, apply a Y phase RF pulse of duration 10 microseconds in amplitude.
Yikes, we have different versions of the problem. Oh, that's interesting. Anyhow, okay, so Y phase. And, but the spin now we're interested in is 3.2 kilohertz off resonance. So Y phase means here is the B1. So we have the B1 field, omega 1 is 25 kilohertz. But we have an offset of 3.2 kilohertz, and that looks like a field along Z, the reduced static field, 3.2 kilohertz. And what the Z magnetization is going to see is the vector sum of the two. So the effective field here has a tilt angle of theta and an effective field strength. So the effective field strength is the vector sum. So what's the magnitude of the vector sum?
Square root 3.2 square plus.
So the square root of 25 kilohertz squared plus 3.2 kilohertz squared. And you can work that out. That comes out to be 25.204 kilohertz. I did the math correctly. And then the tilt angle is going to be the arctangent of 25 over 3.2. And that comes out to be, actually, I did it upside down. I don't know, looks like I did it right. That comes out to be 82.7 degrees. What would that be on resonance? If I did the calculation on resonance, what would I get? 90 degrees. So the tilt angle, I've drawn it much more exaggerated here, right? We're actually quite near the y-axis, just 7.3 degrees tilted up from the y-axis. And now we have our recipe for calculating this. Our first step is going to be to rotate the effective field to the z-axis and then rotate around the z-axis and then rotate back. So we have the initial magnetization. If it starts on Z, it's just the equilibrium Boltzmann magnetization. And our recipe will say, rotate around X by minus theta. And then we'll rotate around Z by what angle?
The effective times the pulse duration.
So the angle is always a frequency times time. And here, the pulse length is 10 microseconds, the on resonance 90 degree. And the field now is 25.2. So we then rotate around Z by alpha, or alpha then omega E times tau P, which will be 25.204 kilohertz times 2 pi times 10 microseconds. And that'll be an angle that will come out in radians, right? Because I put in the factor of 2 pi. But 25.204 is larger than 25. So that rotation angle is going to be larger than 90 degrees or larger than pi over 2. So we will rotate around this tilted frame by a little more than 90 degrees.
It would be about 91.
Pardon?
It would be about 91.
Whatever the calculation comes from, I believe you. And then we rotate back around X by theta. Actually, you'll see if that really is 91 degrees. I can check you. 90.73 degrees.
Yes.
So it'll turn out actually that that's not so different than 90 degrees. So the difference in rotation angle isn't as important as what happens to the phase. So the amount of magnetization that gets into the transverse plane is going to be very close to ideal, but as we'll see, the phase will be different. And this then will be our final magnetization after the pulse. Now, there's 3 ways to solve the problem. One would be we just work out each rotation one after the other, and we can do that either by multiplying matrices together, or we can do it by using our rotations and work out the trigonometry step by step. The other way would be to take the 3 matrices, multiply them together, and then just do one multiplication against our initial vector. That obviously would be a much more sensible thing to do if we had to do this calculation 1,000 times. Then it would be much easier to multiply these once and be done with that. And then the third way is to recognize that this, as we saw, is only 7 point something degrees. So we're very close to the axis. And in the notes, I kind of just showed quickly this approximation that if the angles are small, then matrices commute. So we also should be able to apply the approximation. So I will let you then work this out either way you want to. If you wanted to do this kind of symbolically by hand, right? This first rotation would say we take Z magnetization and rotate around X by minus theta. So we would rotate this way by theta. So our magnetization goes towards the plus Y axis. So after this first rotation, we would have magnetization still on the Z axis. So unit vector K and cosine of whatever theta was, and then plus magnetization on the plus Y axis, sine of theta. And then in the next step, each of these terms has to get rotated around Z. This term is unchanged by rotation around Z. And this term will end up with some magnetization still on the Y-axis and some magnetization that is rotated from Y towards the minus X-axis. And the nice thing here is we always get the signs by paying attention to how our fingers rotate. So we'll end up with 3 terms. And then we have to do this rotation. And depending on those terms, any term that starts on the X-axis will be unaffected by this. Y-axis will be rotated, Z-axis will be rotated. We'll end up with a bunch of terms and then you try to combine them all. And you'll end up with some vector in 3-dimensional space. And you're interested in resolving that into its components. Whatever's left on Z is magnetization that you didn't excite into the transverse plane. That reduces efficiency of the experiment. And then magnetization that's in the transverse plane. On resonance, the magnetization would have ended up on X. If the magnetization ends up somewhere in the transverse plane, or the projection into the transverse plane, we'll make some angle phi with respect to the X-axis, and that represents a phase error in the spectrum relative to the end resonance pulse. You'll be able to work out how much magnetization you got into the transverse plane and what its phase error was. So you can either do it that way, or as I said, you can look up the matrices and the notes, multiply them together, and do the calculation all at once. Are we on time? So let's do the one I'll do with you though all the way through is this approximation. And then when you do the exact calculation, you can see how good the approximation was. So the approximation that we worked out, or that I showed you, says that the 90-degree pulse can be viewed as a rotation by alpha that's preceded by a little delay, tau core, and followed by a little delay, tau core, that is free precession. And tau core is 2 times the length of the 90 over pi. So if we start with Z magnetization, this initial tau core doesn't do anything. That would just be precession, but Z magnetization doesn't precess. So then we have a rotation by 90 degrees. So if we start with Z magnetization, we're going to end up Z magnetization cosine alpha, which is very close to 90 degrees. So that'll be small. And Y rotates to X plus M0 X sine of alpha. Sine of alpha of 91 degrees is going to be almost exactly 1. So we're going to get almost the proper amount of of transverse magnetization. But now we have this rotation that's going to end up giving the phase error. So during tau core, this Z magnetization doesn't precess. So we're just left with this. But here we have M0 X magnetization, sine alpha, cosine tau core times the offset, the 3.2 kilohertz. And X magnetization rotates towards Y magnetization. That'll be plus M naught sine alpha sine tau core. And actually, when I do the calculation, that has to be in radians. So omega has to be 3.2 kilohertz times 2 pi times tau core. So that angle then is the phase angle. The phase then here, the phase error will be tau core times 3.2 kilohertz times 2 pi. Time times the frequency is the angle. And if we plug in the numbers, that predicts what does that predict? A phase error of 7.3 degrees at the end of it. If I did the calculations right, I ended up with this being equal to 7.3 degrees. But to really, and then you'll see, hopefully, when you do the exact calculation, that this simple calculation is very close to correct. And if that's the case, this says that the phase error is proportional to omega. And if we have a phase error that's proportional to offset, that can be corrected with a first order phase correction spectrometer. First order phase correction means a phase correction that's proportional to frequency. So within the limit of this approximation, the effect of an off resonance pulse simply leads to first order phase errors and therefore correctable.
The coincidence that the phase error is equal to the complement of the rectangle?
No.
No, okay.
And if you look back at the notes, where I just kind of quickly went through how one derives this, they turn out to be closely connected to each other.
Right.
So that as the tilt angle moves up, as you go further and further off resonance, and this angle here, the deviation from ideal gets large, then this approximation will start to break down. Because of that agreement between the two. So for today, I think that's all I wanted to do to get you started on the problem set. Maybe we'll do just one more together. Are there other questions about this one? What you have to do it, the exact calculation? The one that's related both of these problems. Later, I forget exactly which problem it is. Let's do the same thing, 25 kilohertz, 10 microseconds, or we could just generalize omega 1 tau pulse or a 90-degree pulse. So on resonance, we're going to get a 90-degree rotation. As we go off resonance, we get a larger rotation angle. If we go far enough off resonance, eventually we'll get a 2 pi rotation. And then we'll come right back to the z-axis and it'll look like we did nothing. So if we have omega 1 tau p equals pi over 2, and we have omega e tau p, we want to be 2 pi off resonance, and omega e is the square root of omega 1 squared plus omega squared. What is omega? What should I do first? Pardon?
Should be
The
square root.
Well, it's always a good idea to get rid of the square root.
Yeah.
So then we have omega e squared equals
Or
omega 1
omega
squared
squared.
plus omega squared.
So right. Omega 1 squared.
What should I do next?
Subtract omega 1 squared.
From both sides?
Both sides. Square root.
Well, let's not do that yet.
omega e is 4 times the strongest. Because omega 1, so I can just.
Yeah.
So,
Right, so I gotta get
Now-
rid of,
well,
have to make use of these equations.
Yeah.
So here, right, tau p is pi over 2 over omega 1. So I substitute in, here I have omega e pi over 2 omega 1 equals 2 pi, or omega e equals 4 times omega 1. Is that what everyone just said? So 4 omega 1, 16 omega 1 squared minus omega 1 squared is 15 omega 1 squared, or omega equals the square root of 15 times omega 1. That means if I have some NMR spectrum, right, and here's C alpha, and here are the carbonyls, here's omega. If I know omega, I can then calculate what omega 1 I need to use. So that on resonance, I get a 90, and the carbonyls look like I did nothing. And then one of the problems goes on to ask you, I think, what's the rule if you want on resonance 180-degree pulse and off resonance a 2 pi rotation? Is also very practical. This is our first order treatment of getting selective excitation of the C alphas relative to the carbonyls. We can do more sophisticated things with shape pulses. For square pulses, is kind of the simplest selective looking pulse. Questions about this? And somewhere between. So what's the tilt angle in that case? We can calculate the tilt angle and so the arc tangent of omega 1 over omega, which is the arc tangent
Given a 1 over square.
arctangent of 1 over the square root of 15,
Yes.
whatever that is. That is not going to be, I think, a negligible phase error. And there are then other ways of trying to compensate for that phase error. And it's not important if we're just asking about the Z magnetization. But if we had transverse magnetization, then the phase effect starts to become important, and it doesn't fit into our simple scheme that we could use when we were close to resonance. Now we're too far off resonance for this T core to work, and there are other tricks that we'll eventually come to. Anyhow, that's a good place to stop. And next week, I'll ask you to do some of the problems, and then I'll post a key. Any questions online? If not, I'll see you all tomorrow. We're gonna have some lights. Oh, you're all still here. Yikes, and while we've been talking, a large number of people have emailed me wanting me to do something for them.